Hey everybody, wanted to spend a little bit of time going over question number one, problem number one in the in-class worksheet. This is going to be really good. My suggestion for doing this is to try to do as much as you can, or do it stepwise, and then check your answer with this kind of video answer key to make sure that A, you get the right answer, but even more importantly, that you're getting the right thought process, because that's one of the beauties that I can do, is I can spend kind of as much time as I need going over the thought process as we do this. And then you can always fast forward and rewind as you need and see fit. Okay, so we have methane and it's decomposing. Now, this is a lot in this first reaction here. Okay, and so what we know is that we have methane, CH4, and that is decomposing into its elements. So we know there's no other reaction here, because decomposition is one reactant forming many products. And we don't know what the products could be, except in this case it tells us that it's going to decompose into its elements. So it's going to decompose into carbon plus hydrogen, and we also know that hydrogen is diatomic. It's part of the Hankel-Briff thing, so that's going to be our reaction, or kind of skeleton reaction. But now notice that it says we need to include states and we need to balance this guy. So let's start with methane. Methane is a gas. How do we know? Well, there's a couple of reasons that we know. First of all, we can just look here and it says gas, so we know that it's like this. The second thing, and maybe the more deeper understanding, is that you see this, and this is a covalent compound, okay? And not only is it covalent, but it only has London dispersion forces. And so those are very, very weak forces, so that means that that is mainly going to be found as a gas at room temperature. Okay, that's a very good indication that that's what's going on. Now carbon is found in nature a lot of different ways, but for the purposes of this, it's just going to be carbon, and we're going to make that solid. And then hydrogen is found in nature as a gas, and you can get that information right off the periodic table. Okay, now we have to balance this guy. I'm going to balance this guy in blue. Okay, and so we're going to say how many carbons? How many carbons? 1 and 1. That's great. How many hydrogens? 4. How many hydrogens? 2. So what times 2 gives us 4? So I'm going to put a coefficient of a 2 there. The next thing that we can do is we can, so that's A, done. So now we need to figure out how many moles of each product there are from this number of starting grams. So in order to do this, we're going to make an ICE chart. Now this ICE chart, notice that I have 3 columns, one for each reactant and product. And so I'm going to put all the reactant values here, the initial, how much it's going to change by, and the equilibrium, and here, and for the products, it's going to go here. I prefer to see this set up like this, so that it's easy for me to kind of just check what your ICE chart looks like. Okay, so now off to the side here, I'm going to put 18.64 grams, because that's how much of this we're starting with. But in our ICE chart, we can only put moles. So the thing that we have to do, kind of rule number 1, is convert to moles. So to convert 18.64 to moles, we need the molar mass. So below the ICE chart, I'm going to get out my paper. You can have separate paper, or you can do it below, whatever. But here we go. We're going to need the molar mass of methane in order to calculate how many moles of this we have. So carbon, there's 1 times 12 carbons, and hydrogen, there are 4 carbons, and each hydrogen weighs 1. Now, I get it, I'm kind of rounding numbers. If you're doing this, I would definitely use however many decimal places the periodic table that you are using is going to give you. So if this gives you, 5 decimal places, use them. If this gives you, if your periodic table gives you 2 decimal places, use them. Okay, so I'm going to plug this into my calculator. Not that I need to, but I'm definitely going to do it just so you can see it. And then and then we're going to go. And so this is equal to 16 grams per mole. Okay, so now we're going to take 18.64 grams, and we're going to grams of methane, and we are going to X-line it, and my X-line is really long here. So we're going to get rid of grams, and then we're going to convert to moles. Notice when we do that, we have grams cancel, and we're left with moles of methane. So for every 1 mole of methane, 16 grams. So I'm going to do this, and when I do this, we get an answer. Now you don't have to multiply by 1 and then divide by 16. You can just straight away just divide by 16. So you get 1.165 moles of CH4. So now we're going to put that right up here, 1.165, and now we don't have to put the unit because moles can be converted. We know that ICE chart has moles in it. We know that all the units for the numbers in the ICE chart are going to be moles. Okay, and so now the next thing that we can do is put in some zeros here. What we know is that this reaction is going to continue to decompose until there's none left. So that's going to be a 0. We also know that in terms of products, these two things are going to be 0 at the beginning. Remember, I is initial, the initial conditions. So this is going to be 0 because, well, in essence, if we already had it, why would we make it? So yeah. Anyways, so we have 0 of this and 0 of this. The other thing is that in the problem we're only given grams of methane. So if we're not given anything else, then we can't assume that there's any else. Okay, so we have to put 0 and 0. Now this helps us out because the most important box is this first change box, and 0. In order to get to 0, we have to subtract 1.165 moles of methane. Okay, and so as soon as we get this first change box, now that means we can figure out this and this and this, and life is good. Okay, so let's now figure out how much carbon we're going to produce. Now, I get it that if you see this enough, you'll kind of be able to do this maybe even in your head, totally fine. But let's do this out just so you know. So we get 1.165 moles of CH4, and that's methane, and that's how much we've used up. But for every mole that's used up, let's see, so now look what I'm going to do. I'm going to put CH4 here, okay, and then I'm going to use the balanced chemical equation to do this. So what's the coefficient of carbon here? 1. What's the coefficient of carbon here? 1. So what that tells us is that for every 1 mole of methane that we make, or that we have, we're going to make 1 mole of carbon. It's a 1-to-1 ratio. So notice then the units cancel out, and so we get methane canceled, and now we're left with just moles of carbon. And so the answer here is 1.165 moles of carbon. But now this is where you have to use your brain just for a second, is that if we're starting with 0, that means we're going to make carbon, plus it's a product of the reaction, so we have to add 1.165 moles. Okay, now for the second one, okay, we're still going to use 1.165 moles of CH4 methane. Okay, but now we're going to go from methane, and instead of carbon, we're going to go to H2. Now, a little more tricky, not tricky, but a little more in-depth here, is that we have 2 moles of hydrogen gas for every 1 mole of methane. So in order to reflect that, we're going to say 2 moles of hydrogen gas. We're going to put 2 hydrogen gas for every 1 methane. And now when we do that, I'll put that in the calculator in a second. So we're going to cross off methane, and notice we're left with moles of H2. So we do 1.165 times 2, and when we do that, we get 2.33 moles of H2. So now we come up here, and we put 2.33 moles, and we are adding that to 0. So now we get 1.165, because 0 plus 1.165 is 1.165. Okay, and then 0 plus 2.33 is 2.33. If I can draw that well. And so now from there, we can, we've answered question letter B. So now we have to convert this back to grams. What is the units of our ICE chart? The units are in moles. So how do we go from moles to grams? Well, we have to use our molar mass. So if we're going to use molar mass, we have to know how many moles of each we have. And so that's answers that we have right in our ICE chart. Notice we have 1.165 moles of carbon, and we have 2.33 moles of hydrogen. So we're going to go 1.165 moles of carbon. We're going to X-line this guy, and we're going to put moles on the bottom, grams on the top, and we're going to go to the periodic table, and we're going to see that for every 1 mole of carbon, it has a mass of 12 grams. So we do 1.165 times 12, and that's going to equal 13.98. So that's 13.98 grams of carbon. Moles cancel. We're left with grams of carbon. Units are our friend. And so now, just kind of below, just because I'm going to write 13.98 grams. Okay? Because it's not part of the ICE chart, just like this mass isn't, because ICE charts are only done in moles. Okay? Now we do the same thing for the next one. We do, 2.33 moles of H2. X-line it. We go moles to grams. Okay, for every 1 mole, let's see, H2, okay, I'll put that under here, H. For every, there's 2 of them, and each have a mass of 1, so that makes the molar mass of this 2 grams per mole. Okay, now, don't get confused because there's a 2 here. Okay, that coefficient does not play a role in the molar mass. You should not use this coefficient because the formula is H2. It's not 2H2. Okay, it's just H2. So here we're going to put a 2, and so when we do that, we multiply it, we get 4.66 grams of H. I'm going to put this below, again, the periodic table, and so it's 4.66 grams. And now notice, now we're going to check our answer, because the law of conservation of matter says whatever we start with in mass is going to equal whatever we end with in mass. And so I'm going to go 13.98 plus 4.66. and we get 18. You get 18.64 grams, and that's how much we end with, which is equal to what we started with, so that checks. So that is how we do that